Hi, this is part two to the lecture for chapter 12. Share the screen. Okay. So in part one, we estimated the coefficient of A and B that is here, and I'm gonna go do the Excel analysis, regression analysis. Go to data analysis, regression. Press OK. This is all populated. Let me erase all this. So all right. I think when you open it, it should look like this. For the Y range, you want to put in the Y variables. Scroll. These are the Y variables. I'm going to stick in also the header. For the X range, I'm going to put in the X variables, and including the headers. The headers are the label. Click on label. Confidence interval is something I'm going to play with in this video. So I'm going to set this to something. Let's put 99%. And the output, I'm going to click right here. So the output starts here and it spans to the right and bottom. And there it is. That's the output. I'm going to format it a little to make it cleaner to look at. Bear with me. This is the percentage. Standard errors, stats. Okay. P-values are percentages. And these are all numbers. I know you don't know what some of these things mean. Don't worry about it. So out of all of this, we basically, let me just pause. Okay. We basically found these guys. Okay, the coefficient estimates. We found that last video here and right here. We found it both using the quote unquote hard way of hard calculating it and the quote unquote easy way using the summary, using the Excel regression uh, uh, kind of software pack that's part of the data analysis tool pack of Excel. Our goal is for today, is to go over most all of these other cells. Okay, all of these right here. So what I'm going to do is highlight everything. Okay? And every time we go over something, I'm going to unhighlight it. Observations is easy. There's 10. 5, 6, 7, 8. There's 10 of them here. So that's what this is. So let me unhighlight that, get something out of the way. Okay, so we just covered that. And we covered these last lecture. All right. So now let's see what we have to do. Okay. What we're going to learn about is this thingy called total SS and SSR and SSE. Okay. This is right here. This is section 2. Total SS is equal to SSR plus SSE. Total SS is the total sum of squares. And that is S, Y, Y. And that's basically each individual Y that we observe here, the data, minus the average. Okay. And that is squared and you sum it over all of the students in this case, all of the data. Okay. And this is the sum of the difference in the actual y and the average. Okay? SSR is the sum of squares due to regression. This is estimated y, basically the y that is the output from our regression model that we created, minus the average squared, and you sum them all. And this is the difference in the model y and the average y, and it's a measure of the amount of variation explained by the model, our regression model with the one independent variable. SSE is the sum of squares due to error. This is yi minus, this is the actual data value, yi minus the estimate from our model, squared, and sum. This is the sum of the actual minus the modeled y, and it provides the measure of the error of our estimated equation. Okay, this is the part that's not explained. It measures the residual variation in the data that is not explained by the model. I'm going to calculate each of these using the data. We're going to hand calculate that. And then I'm going to show you, oh, by the way, it's spit out already in our summary output here. Okay. So what is visually, what does this look like? Here's our red data points are the, the math achievement score and the final calculus grade data that we're given. This is the data. This is the regression line that we estimated using, that's the model we estimated. That shows you the linear relationship between the math achievement scores and the grade you get in the calculus final. So this is the, and for some value of x right here, okay? Total sum of squares is yi minus y bar. So it's the actual y minus the average right here. So this whole line is the total. This upper part, the difference between yi and yi hat, is SSR. Okay, yi hat minus yi hat minus y bar. No, I'm sorry, that's this right here. Sorry. This is SSR right here, yi hat minus y bar. And this right here is yi minus yi hat, I minus yi hat. That is SSE. Okay? This is the model. This is the actual data point. The difference is the error. This is the model. This is the average. This is explained by the model. The total SS is this. Okay, so let's calculate that here. Okay. So the first one we're going to calculate is total SS. Okay, total SS. And this is yi minus y bar. Okay, so this is equal to, parentheses, the yi here minus y bar right here. We calculated that. I'm going to put dollar signs around the y bar so that doesn't move while I scroll the formula down. And then we got to square this thing. Okay, what I just did. And then I'm going to copy the formula all the way down to here. Okay. And then we're going to sum it. So total SS should be 2056. Okay. Now let's see what SSR is. SSR. And that's the sum of yi hat minus the average. What is yi hat? yi hat is the estimated y given our model. So that is the y-intercept, A, plus B times X. And as we need to lock in place, anchor the intercepts, okay? Minus this whole thing minus y bar, the average, and this is the average. Okay, and that whole thing has to be squared to the squared. Okay. I'm going to copy and paste the formula down. Sum it all. Yep. Let's check a random formula to make sure we did it correctly. Yep, we're using, oh no, we're not. Something got scrolled down to here. So we're not doing something correctly. So let's look at the first one and see what we didn't do right. Oh, we need to anchor the Y bar. We forgot to anchor that. Let's anchor it. Copy the formula down. Okay. Make sure we did it correctly. So this one doesn't need to be anchored. This one needs to be anchored, this and this. Looks like we did it correctly. So SSR should be this number. The next one is SSE, and this is equal to YI, which is this number YI, minus the estimated YI hat. And again, that one we need to calculate, which is A minus B times X. And these all has to be anchored except for X. Okay. And the whole parentheses, this thing has to be in parentheses to the square. Okay. Scroll that down. Take the sum of it. Okay. All right. Check one of these to make sure we didn't mess it up. Okay. Looks like it's good. I don't think this is good. Let's make sure we didn't mess something up. This is yi minus sum of a minus b times x, the whole thing, parentheses. Oh, I'm sorry. This is plus. Plus. Yeah, sorry about that. This was a plus b times x, not minus. So I think I did it correctly. Yep. Okay. So I calculated all these, okay? And that's how you would have to do it by hand if you do not want to use Excel, okay? But you could actually use Excel and these would be all calculated for you, okay? Let's go look at it here. They're right here. This is total SS, that's called total, okay? And I'm gonna relabel it total SS. That's what this is, 2056. Let me open up the screen a little. 2056 right there. SSR is it's 1,400 at 49.97, 1,449.97 there. And SSE is 606.03, 606.026. Okay, which is, yes, that's it. Okay, so we just found these right here. Okay, you don't have to calculate it, it's there already. Okay, let's move on. All right. So here are some other things that you're gonna need to calculate in the future. These stuff. Some of this we've already did, like SXX. That's sum of xi minus x bar. That's right here. Anyway, okay. Keep going. All right. Now, each of these variation sources, each of the various sources of variation, when divided by the appropriate degrees of freedom, gives you an estimate of the variation in the experiment. Okay, the important one that you need to know from what I just said is the mean squared, or MS, which is the SS divided by degree of freedom. Okay? So mean squares is SS divided by degree. Mean square is SS divided by degree of freedom. And the important one is the mean square for errors, okay? Which is SSE divided by the degree of freedom n minus 2. Okay? And this gives you the unbiased estimator of sigma squared. This is our sample estimate of the variance. Okay? That's MSE. So let's calculate that. That's actually right here. Mean square MS, that's the mean squares. And we have one for mean square residual, and we have one for mean square um, residuals and regressions. This is regression and this is residuals. And all you have to do is divide the SS by the degree of freedoms, and that's how you get mean square. Let's calculate that right here, right above it, mean square. And we'll do regression and residual. And mean square regression is this one, SS regression divided by degree of freedom. There it is. That's the same as that, which is the same as that because it's just divided by 1. Mean square residual is SS residual, okay? Mean square error, SSE for error term, divided by the degree of freedom is 8 because it's n minus 2. 10 is the observations, minus 2 is 8. And there it is. It's the same thing. So you don't even need to calculate it, they give it to you. And that's this right here is our unbiased estimate for the variance term, which we are going to use later for calculating standard errors, okay? So instead of doing this, I'm going to put in S squared, and that is just this guy right here, okay? All right, so there you calculated that, okay? And here's how to do it, kind of the long way. We just did it the long way. And here it just shows you what we just did. And just shows you what we found. Okay, let's move on to section 3, testing the usefulness of the linear regression model. Inferences about beta, the slope of the means. Okay, we could actually find, and we could actually do hypothesis testing of both alpha and beta. Okay, but we're focused more on beta because we want to know, well, what does beta give us? That's a slope line, and that's basically the causal relationship between x and y. How does y get impacted by one movement of 1 unit of x. Okay, so beta is actually really important. Okay, all right. So the mean is the expected value of the estimated b is equal to the population parameter beta. Standard error for b is equal to the true population variance divided by SXX. Okay, and you square root it. Okay, let me scroll up a little. And that is equivalent to the estimated sample variance that we just estimated divided by SXX, which is equal to the mean squared error divided by SXX. So let's calculate that. The standard error for B, which is right here, should be standard deviation divided by SXX. Okay, the standard error of B, calculate that. And this is this guy divided by SXX. And we calculated SXX right here. Okay, it's xi minus x bar squared and sum of that. And there, see if that's it. Okay, and we got to square root this number. Got to square root it, sorry. And there it is. The same number. So we don't even need to calculate it. Yes, you should know what the formula is for the test and whatnot. It's open notes. It's right. This is the formula, but it's given to you right here. Okay. So I'm going to erase this one for now. This one is right here. Okay. All right. So that's the standard error right here. The impact of the independent variable x on y is measured by b. I just went into that. If the true effect of x on y is 0, then any change in the independent variable x does not change y, or has no effect on y. X has no effect on y. If beta is equal to 0, that's basically saying x and y are independent. That's actually the most important hypothesis test that we will do. Does x have an impact on y? Testing testing the hypothesis that b is equal to 0 versus b is not equal to 0 is the test that is default in Excel. Okay, and that is shown right here. Okay, is there a linear relationship between x and y? This is so the important test is whether b is equal to 0. This two-tailed test right here, where b is equal to b naught, which is b naught being 0, and b is equal to not equal to b naught. Okay, but this is the generalized form. If you want to test beta is any equal to or less than equal to any number or greater than equal to any number b naught. This is the generalized form. This is the test statistic. B is equal to b, the estimated b, right? Which is right here, minus b naught divided by the standard error. Okay, that's the test statistic. There's the test statistic right there. Okay. Okay. So let's calculate that. Test stat. And we're calculating the test stat where beta naught is equal to 0. So the test statistic, the numerator, is the coefficient, oops, equal to the numerator is the coefficient minus b naught of 0 divided by the standard error. Okay. 4.375, 4.375 right there. So that's the test statistic right there. When B naught is 0. Okay? This is T distributed. It has a T distribution with n minus 2 degrees of freedom. Okay? And you reject H naught if in the one-tailed test, if T is greater than T of alpha, so the test statistic you calculate is greater or more extreme away from T, the critical value, T of alpha, or the T being negative, the test statistic being negative, is more further away from 0, is less than the minus T of alpha. And the two-tailed test is T is greater than T of half alpha, or T is less than, this is wrong, less than T of half an alpha, okay? And I'm going to put the negative sign here, just so we know that those are negative numbers, okay? I'll upload this because it's negative. It's wrong. All right, or the p-value. P-value is less than alpha. Okay? So that test is already included, which I just alluded to earlier, in here. Okay? It's right here, the p-value. They give you the p-value right there. Okay? And right now, the p-value shows 0.2365. That is less than any conventional alpha of 1, 5, or 10%. This is less than 1%. That means since the p-value is less than any conventional alpha of 1%, the most extreme one, we could reject the null hypothesis that B, or beta, in this case, the population parameter beta, is equal to 0. Okay? So basically we're saying, yes, math achievement scores do have an impact, statistically significantly have an impact on final calculus grades. Okay? You could do the same kind of testing with the y-intercept. That's less important because that's basically saying, well, what does that say? Even if you didn't take the math achievement test, or you got a 0 on the math achievement test, you should get about 40% on the calculus exam. Okay? And we see that the p-value is, yeah, it shows that it's 0.1366 or less than 1%. So we could reject the null hypothesis that the y-intercept is 0, and it's likely differentiated from 0. And so 40.78 probably may be the real value of what you should expect if you got a 0 on the math achievement test. Okay. All right, let's move on. This is what we just did. This is the example with the pizza. Confidence interval. Okay, so there's a confidence interval building. Yes, we could create a confidence interval of our estimate of beta, okay, which is point plus or minus the margin error. The point estimate is just B, which is right here. And the margin of error is T of half an alpha times the standard error. Okay, so let's build that. So point estimate, this is equal to this guy. Okay, and the margin of error is equal to T of half an alpha and the standard error. Oops, and the standard error. Standard error we already know is this dude right here. T of half an alpha, that's a T dot. What is alpha again? Well, we didn't find a 95% confidence interval. So let's do it with 95%. So alpha is So confidence interval is 95%. That's what we're going to build. Okay, find a 95% confidence interval. So alpha is equal to 1 minus 95%. So half an alpha is equal to alpha divided by 2. It's 2.5%. So T of half an alpha, T dot INV. And then we got to put in 1 minus half an alpha because the half an alpha is in the tail. So we got to put in Excel works by you got to put in the 97.5% in. The degree of freedom is n minus 2 degrees of freedom. And n was 10, so 10 minus 2 is 8 degrees of freedom. Okay. So the margin of error is T of half an alpha times the standard error is this number. And I'll just shrink it because it's really ugly long. And then let's build this. We have an upper point, lower. Point is our point estimate, our beta estimate. The lower is point minus the margin of error. The upper is point plus the margin of error. So this exercise here, 12.3, should give us this number. Okay. The resulting 95% confidence interval is 0.63 to 1.17. There it is. Okay. And that's actually provided here. Here. These are our two confidence interval we're building. Okay. Why is there two like this? So here's the lower 95 and upper 95. Those are those two numbers right here. Oh, there they are. Okay. These two are down here. And I don't know if you recall earlier, I even specified a 99% confidence interval. Okay. So right there, when I basically told Excel to do a 99 earlier. So let me show you that. When you go to data analysis, regression, and press OK. Okay. This is what I put in earlier. Confidence, I put 99. Excel will always give you the 95s. I don't know why they pick 95, but they will always give you the lower and the upper 95%. But Excel knows that you might want something else. 99, 83, 74. So you could put in here some other customized value, 78. Okay. And then what it will do is give you another one. So let's do this. Output range. I'm going to put it right here. Press OK. And nothing here will change except for these two right here, which is 78. Okay, compared to 99. Okay? Nothing else will change other than this. All right. So I'm going to delete this. I think 99 is a reasonable one. You could do a different one if you want. I just picked 99. Okay. So again, this is for the pizza example. I did two, 95 and 99. Okay. Analysis of variance F-test. So like we learned in chapter 10, at the tail end, we learned about the F-test. They even have an F-test here. There it is. Okay. So what is the F-test here? It's not the ratio of the variances. This is actually something different. Okay. Let's talk about this. The f-test here is FMSR regression divided by MSE or error. So let's just calculate this guy. I'm going to calculate it right here. F. This is equal to MSR divided by MSE. It should be 19.141. There it is. Okay, right there. That's what the F value is. MSR divided by MSE. That's what this is. Okay. Now, what does it give? MSR is, okay, this gives you basically the significance of of all of the betas in the model. Okay, basically gives you the significance of the model. Is the model statistically significant? Okay, not in magnitude, but statistical significance. Okay, so right here, this just tells you how to calculate it. All right. This isn't for chapter 12 world. This is basically equivalent to testing whether the null hypothesis of beta equal to 0. Okay. So this is an equivalent test of beta being equal to 0. The f-test is used instead of the f-test using the f distribution is used instead of the t-test and the t distribution. It is slightly different when you have more than one independent variable like you would have in chapter 13 world. There, you're testing whether you're testing the whole series of independent variables, whether they are equal to 0. Here, we only have one, so it reduces down to just a simple test of whether beta is equal to 0. Okay, here's the testing procedure. B is equal to 0, B not equal to 0. Okay, and you're using the F statistic instead of the T statistic. Okay, and the rejection criteria is the same. P-value is less than alpha. F is greater than F of alpha. Okay. And I want you to notice something. The value of the F statistic is equal to T statistic squared with identical p-values. P-value and this p-value are identical. Okay, those are the same. Okay, let's see if they are identical, equal to this. And it is. They are identical. Excel says so. And the F stat is equal to T statistic squared. Well, let's do that. Let's get the T statistic, square it. Oops, big number. And that is equal to the F stat. This equal to this guy. Yep, it's true. So it's basically the same thing. Okay. So that's what the F test is. It's just doing the T test, here in chapter 12 world. Let's move on to the next thing to learn about. We pretty much learned about everything here, and that is the coefficient of determinants. Okay, the coefficient of determinants. Okay, remember though. Okay, so we have the correlation coefficient, this R thingy, and we have something called R squared. So let's talk about these things. R is Sxy divided by Sx times Sy, where Sxy is the covariance between x and y, and Sx is the standard deviation of x, Sy is the standard deviation of y. Okay, so let's calculate that using this data. Okay, so we have Sxy, Sx, Sy. This is the covariance dot S, and here's 1, comma 2. Okay, this is the variance. This is standard deviation, sample standard stdev dot s of the x's, and this is the stdev dot s of the y's. So R would equal to this guy divided by, oops, okay, let me see. R is equal to this guy divided by this guy times this guy in the denominator. And we got 0.8397 blah, blah, blah. And there it is right here. Multiple R is just a complicated way of saying it's R. We have R calculated right here. Okay. Let me clear this. Well, the coefficient of determinants is R squared. All right, so equal to, is it just squared R to the squared? Yep, that's what R squared is. It's just the correlation coefficient squared. And there it is right here. But they're saying, look, there's another way of calculating it. SSR divided by total SS. SSR, okay, SSR, let's just calculate R squared. This is SSR right there, divided by total SS right there. And again, that's the same number as this. That's just R squared. Okay? So there's two ways of calculating. Just square the multiple R's or divide SSR divided by total SS. That's what this is. Okay. And the coefficient of determinant, or R squared, provides the proportion of the total variation that is explained by the linear regression model. Okay. It takes a value between 0 and 1. This takes a value between 0 and 1. And if it's equal to 0, then that means SSR is 0. And that means SSE, this, sum of square error, is equal to as total SS. Okay, I know I put SST here, it should be total SS. Now, that means that the model is not explained, does not explain the data. That means the model does just horribly fits. Well, the 0 means it does not fit. If it's equal to 1, then SSR divided by total SS is equal to 1. Okay, they're equal. So I'll just do total. And that means SSE, sum of square error, is equal to 0. The model is a perfect fit. Okay. So you want this number to be as close to 1 as possible. Okay. There's something else called adjusted R square. There's a way to manipulate the R square by putting more variables in. Well, we're not going to get into that right now. We might get into that later. For now, just know that you want this to be as close as. That means their model that you created is a perfect fit to the data. Okay, and this is again another way of writing out the formula: SSR divided by total SS. Okay, and here's an example. And we are done for today. We're going to stop here and start up at interpreting the results of a significant regression in the next lecture, part 3. Have a good day.